Okay, we're back with another video on this idea of velocity and other rates of change. So I'm titling this Position, Velocity, and Acceleration. And we're going to start with this worksheet right here. And we're going to go through the problem on the front and the back and then move into some other notes. So this problem says, the position in inches of an ant moving along a horizontal string at any time t seconds is given by S of t equals negative t squared plus 4t minus 3. So S of t is our position. So this models the position of the ant. Part A says, write an expression for v of t. Okay, so we have to know the order of derivatives. So from our learning last week, or the other day, the order of derivatives goes S to v to a. So position to velocity to acceleration. So if you take the derivative of position, you get velocity. If you take the derivative of velocity, you get acceleration. So to write an expression for velocity, I'm simply going to take the derivative of position. So v of t will be equal to negative 2t plus 4. And since it's a velocity, I'll write that as inches per second. Okay, part B, write an expression for a of t. So all I have to do is take the derivative of v. So a of t will just be the derivative of negative 2t plus 4, which is negative 2. And that will be inches per second, or inches per second squared. Part C, what is the instantaneous velocity of the ant when t equals 2 seconds? Well, v of t is instantaneous velocity. It's the slope of the tangent line on S. So all I'm going to do for this problem is plug t equals 2 into v. So v, instantaneous velocity at 2 seconds, is negative 2 times 2 plus 4, which is going to equal 0 inches per second. So that means the ant is standing still at 2 seconds. He's not moving. He's moving 0 inches per second. Okay, part D, what is the ant's displacement? Displacement after the first 3 seconds. Okay, displacement is an interesting little concept, and if you don't take physics, it might be a new concept to you. Displacement is just how far you are from where you started. So when it asks, what is the ant's displacement after the first 3 seconds, what it's really asking is, hey, after 3 seconds go by, how far is the ant from where he was at 0 seconds? So this is why you use this formula. You do your position at your ending time, which is 3 seconds. You do your position at your starting time, which is 0 seconds, because the first 3 seconds imply 0 to 3, and you find the difference. If you want to know how far he is from where he started, subtract these two positions and that'll tell you. So all I'm going to do is put these values up here for my S. So S of 3 will be the opposite of 3 squared plus 4 times 3 minus 3. And then I'm going to subtract position at 0, which is the opposite of 0 squared, plus 4 times 0 minus 3. And when I do that math, the first parentheses here is going to be a negative 9 plus 12 minus 3, which is 0. So this right here is 0 minus, and this guy right here is going to be negative 3. So I have 0 minus negative 3, which is positive 3. So the final answer here is going to be 3 inches. So the ant's displacement is 3 inches. That means he's 3 inches farther along from where he was at 3 seconds than he was at 0 seconds. Okay, and last but not least here, what is the ant's average velocity? Average velocity on the time interval from 0 to 3 seconds. Okay, there's a difference between average velocity and what we did earlier, instantaneous velocity. So here's the difference. Let me draw a little graph here. If you think back to when we first started this chapter on derivatives, we drew the PQ graph, and it looked like this. We started by drawing a secant line through P and Q. And we found the slope of that secant line. Well, the slope of this secant line is going to equal average velocity. Because velocity is the rate of change of the S graph. So if this is a position graph, then the slope of this secant line is going to give me the average velocity from A to B. The average rate of change, because I'm doing it over an interval of time. Now, the slope of the tangent line is going to equate to instantaneous velocity. So if I were to draw a tangent line at P, that's going to be the instantaneous velocity at P. This question asks for the average velocity. So we're going to use this formula. Position at time B minus position at time A over time B minus time A. So it's your position at your ending time minus your position at your start time divided by your ending time minus your start time. So what ends up happening is if this is an S graph, then the coordinates at P are A, position at A, and your coordinates at Q are B, position at B. So you can see the slope coming to life. S of B minus S of A all over B minus A, and that's giving me the slope of the secant line in whatever units. In this case, it would be inches per second for the ant. So, since my time interval is from 0 to 3, my A is 0 and my B is 3. So this formula becomes position at 3 seconds minus position at 0 seconds all over 3 seconds minus 0 seconds. And if I use my S of 3 minus S of 0 from up top here in letter D, I already know that that's 3 inches. So I'm just going to steal that. Divided by 3 minus 0 is 3 seconds of time. So from 0 to 3 seconds, he went 3 inches. So we're going to say that the average velocity of the ant then is 1 inch per second. And that's going to be that. Okay, very good. Now we're going to flip this over. And boy, did I bleed through there. Let me go grab another one. My Sharpie bled through. Okay, video did not take account for bleed through, but here we are, number 2. Okay, this one's going from a more graphical standpoint. This says the figure below shows the velocity in meters per minute of a car moving along a coordinate line. Okay, so all of the y values plotted on this graph are velocities, directed speeds. So let's take a look here. If my velocities are positive, which all of these are, now granted they change, they increase, they stay the same, and then they decrease, but all of these velocities are positive velocities. That's going to indicate rightward movement. Then when I switch and come down to negative velocities, that's going to indicate leftward movement. So let's take a look at these. Part A says, when does the car reverse direction? Well, that's pretty simple because the car is going to reverse direction when it stops and the velocity is 0 and it changes direction from positive to negative. So I'm going to say the car changes direction at t equals 30 minutes. And the reason I'm going to give is velocity is 0 and changes from positive to negative. Okay. Part B, when is the car moving at a constant speed? Well, you can see that pretty easily right here. The velocities are unchanging between 10 and 15 minutes, so let's go ahead and just answer that quickly. Between 10 and 15 minutes, the velocities are unchanging, so we'll call that a constant speed. Okay, next they're asking us to sketch a graph of the car's speed. Well, speed and velocity are very similar. It's just that speed does not indicate direction. Speed is actually the absolute value of velocity, so let's jot that down. Since speed equals the absolute value of velocity, all we have to do to graph speed is take the graph of velocity, and anything that's negative, we're just going to reflect it upward across the t-axis to turn it positive. So what I'm going to do is, in a different color, I'll pick this sort of orangey color. I'm going to put C above, in red, the graph of speed versus time will look like this. This will all stay the same, but this part is going to reflect up. So this is going to come up here and down. Now what's great about a speed graph is it tells you a lot really quickly. So the car speeds up, stays the same speed, slows down. Speeds up, slows down. It's just that at this point where I'm speeding up in the leftward direction, and I'm slowing down in the leftward direction because I'm underneath. So the velocity will give me the direction. Hey, I'm speeding up left, I'm slowing down left, where speed will just give me speed up, slow down. It won't tell me anything about direction. Last but not least here, sketch the graph of the car's acceleration. Okay, since acceleration is the derivative of velocity, I need to analyze the slopes of the tangent lines on the velocity graph and display those slopes here on the acceleration graph. So I'm going to call this time and A of t for acceleration. And what I'm going to have to do is go back to my original graph and analyze slopes. So if you look at this as a piecewise function in 1, 2, 3, 4 pieces, then I have 4 slopes. The first slope, it looks like I'm going up 60 and over 10 for this segment here. So between 0 and 10 minutes, my slope is positive 6. So between, come down here, so between 0 and 10 minutes, my slope is positive 6. Then, between 10 and 15 minutes, my slope is 0. So between 10 and 15 minutes, my slopes are 0. Then, between 15 and 40 minutes, my slopes switch to negative 4. So between 15 and 40, so 10, 15, 20, 25, 30, 35, 40, my slopes are negative 4. And then from 40 to 55, if I calculate the slope of that segment, it's 2 2/3. So I'm going to come up here 2 2/3, about right here, and take that out to 55. And again, I'm calculating those slopes off of the graph up here. So here my slope is 6. Here my slope is 6. Ooh, it's not coming out so good. Here my slope is 0. Here my slope is negative 4. And here my slope is 2 2/3. If I just calculate rise and run. And I'm just modeling that down here on my acceleration graph. Notice I'm non-differentiable. That's what these open dots are. I'm non-differentiable at all the corners. See a lot of sharp corners up there, which is why these holes are opened. All right. So that's going to end this video. There's going to be one more video in this section, so tune into that next.